Welcome to the new lecture on Newtonium and non-Newtonium fluids. Compressible versus incompressible fluids. Blood is a non-Newtonium fluid. Ketchup is a non-Newtonium fluid. Toothpaste is a non-Newtonium fluid. Water is a Newtonium fluid. Right? Compressible, incompressible. Compressible. So, fluid I said. Gas is also a fluid which can be compressed. Gas can be compressed. Incompressible. Liquid cannot be compressed. So, this is what we will try to see in detail in this lecture. So, the content will be introduction, then we will try to see Newtonium fluids, then its application and why are non-Newtonium fluids at all exist and what are its application, what are the different types of non-Newtonium fluid, its application, compressible fluid and incompressible fluid. Fluid are materials who deforms continuously when subjected to a shearing stress, no matter how small. The classical fluid mechanics, as treated in the sources, primarily deals with fluids and excludes material like clay or mud, which are studied in rheology. So, in classical fluid mechanics, we always look at the primarily deals with fluids. Viscosity is a very important property in fluid. Viscosity is an important property of fluid. Experimental observation show that when a fluid is sheared between two plates, there is one plate, there is another plate. Now, what you do is you put a droplet here and this is sheared. Experimental observation shows that when a fluid is sheared between two plates, the shear stress is proportional to the rate of shearing strain for common fluids like water and oil. The constant proportionality in this linear relationship is the dynamic viscosity. So, what we are trying to say, tau, and then I try to say strain. So, if it is linear, experimental observations show that when a fluid is sheared between two plates, the shear stress is proportional to the rate of shearing strain for a common fluid. Okay. So, the relationship can be expressed as tau is equal to mu into du by dy, where tau is the applied shear stress. Du by dy represents the velocity gradient. This is a gradient. From here, this is d, and from here to here there is a there are delta t, right, delta d. So, these are gradients. So, du by dy represents the velocity gradient. This is nothing but velocity gradient, which is equivalent to shear strain rate d theta by dt for a common linear fluid, where mu is the viscosity coefficient, which is constant of proportionality in this relationship. So, mu is a constant of proportionality, viscous coefficient. Why water is called as a Newtonium fluid? Water demonstrates a consistent linear relationship between the applied shear stress and the resulting rate of strain, characterized by a dynamic viscosity at a given time. It fits the definition of a Newtonium fluid, unlike the substances whose viscosity changes with the shear condition. For example, you have a drop of tomato ketchup which is there, honey which is there. It tries to continue to stay in its position like a dot itself. So, when you try to push it, then it tries to move little bit and again it freezes. So, unlike substances whose viscosity changes with the shearing condition. Okay. So, here you can see the shear stress versus shear strain. For air at 60 degrees, it is following a linear one. Then at water 100 degrees Fahrenheit, friends note down it is Fahrenheit. Water at 60 degrees Fahrenheit, and you try to take crude oil with 60 degrees Fahrenheit. So, you see how the viscosity changes. The actual value of a viscosity depends on a particular fluid. For a particular fluid, the viscosity is also highly dependent on temperature. As illustrated in the figure, you can see in the figure temperature. As illustrated in the figure, with two curves of water, fluid for which the shear stress is linear related to the shear strain, and this is designated as Newtonian fluid. Fortunately, most common fluids, both liquid and gases, follow Newtonian fluid. So, if you see in this diagram, shear stress tau, shear strain rate is given here. So, you can see here the viscosity for a pseudo-plastic material. This is for Newtonium, which we saw directly proportion. And there are fluids wherein which it tries to stiffen as and when you are applying shear stress to it. So, those ones are called as diluent fluids, where you apply shear and then the viscosity changes. So, here these material are high viscous and these are low viscous. You have ideal plastic, Bingham plastic, wherein which it tries to continue to be in its constant till you apply a particular shear rate and the shear stress, and then it increases. The shear strain rate is almost constant and it then goes. So, this is called as ideal plastic, which is otherwise called as Bingham plastic. So, it behaves more like a solid when you go down. When you go down, it behaves more like a liquid, and when you move to the other end, it behaves like a solid. So, we are always focused more towards Newtonian fluids. The other one, all the other things are called as non-Newtonian fluids. Diluent fluid, pseudo-plastic and ideal plastic are all non-Newtonian fluids. They do not follow the proportionality. Okay. If you have a medium which is mixed with abrasive and a viscous material, if you are trying to push it inside a bottle, so that one is called as ideal solid, and then initially it follows to a high shear stress, there is no improvement. So, that means to say it is almost like a solid, it is there. Moment you push it harder, then it becomes it starts deforming and getting inside. So, this is Bingham plastic, and you have pseudo-plastic. So, Newtonian fluids applications like water, air, mineral oil are primary choice in heat exchanger and in cooling systems. So, in electronics, HVAC and industrial reactors, because the stable viscosity and it has a high heat transfer efficiency. So, that is why we always use Newtonian fluids. In mixing tanks and industrial reactors, Newtonian fluids are preferred since the viscosity does not change with shear, allowing uniform mixing, and the temperature distribution and accurate process control can happen always in a Newtonian fluid. When you are trying to mix juice or something, you put a syrup and then water, then you mix it. So, mixing happens in a Newtonian fluid, it can try to lead to accurate process control. Newtonian drilling fluids and mud are employed for drilling operation, providing lubrication, cooling and the pressure balancing in oil and gas wells. So, they use Newtonian drilling fluids. So, all these things are Newtonian fluids. Your water, mercury, olive oil, honey, mineral oil, gasoline and milk, all these things are Newtonian fluids. What are non-Newtonian fluids? Non-Newtonian fluid is defined by the fact that it does not follow the linear relationship when the shear stress is applied, and the resulting strain rates that characterizes a Newtonian fluid. Non-Newtonian fluids, however, has a non-linear relationship between shear stress and the shear strain rate. This means that the resistance to flow is not a constant. So, it changes with respect to time and temperature. The slope of the nonlinear curve at any point on the shear stress versus shear strain rate plot is referred as an apparent viscosity. So, whatever you take here is called as an apparent viscosity. So, there are types of non-Newtonian fluids. They are dialent, pseudoplastic and Bingham plastic. These are shear thickening fluids. Their resistance to flow increases as the strain increases. Moment you strain it, it becomes more solid. Pseudoplastic, these are shear thinning, these are shear thickening. These are shear thinning fluids. They become less resistance at higher strain rates. Very strong thinning is called as plastic. Right? Pseudoplastic, shear, when you are trying to apply shear, if the fluid becomes solid, it is called a shear thickening behavior. This is dialent. Bingham plastic is a substance that requires a finite yield stress before it starts to flow. You keep on pushing, it resists. After some point of time, it starts flowing. Those things are called as Bingham plastic. The source describe yielding followed by a linear behavior in some case, though non-linear flow after yielding has occurred. So, this is dialent, pseudoplastic and Bingham plastic. They are all non-Newtonian fluids. Why cornstarch and water mixture is a non-Newtonian fluid? The cornstarch and water mixture is specifically identified as the shear thickening fluid. You mix it, it gets thickened. For shear thickening fluid, the apparent viscosity increases with the shear shearing rate. As the mixture can behave like a quicksand, they become harder or more resist to flow when they try to move quick through them. So, it is a non-Newtonian fluid where shear thickening happens. The figure illustrates this behavior, showing the plot of the shearing stress versus rate of shear strain for a shear thickening fluid is not a straight line. So, you can see here is not a straight line. It is not a straight line. The slope gets steeper as the shear rate increases. So, application of non-Newtonian blood is a shear thinning fluid is critical in medical diagnosis and analysis as the variable viscosity affects the circulation and considered it in designing a biomedical device like artificial heart valve and blood pumps. Then drug delivery systems and tissue engineering utilize a smart non-Newtonian fluids that adapt to psychological conditions. Many food are non-Newtonian fluids with Taylor flow properties for desirable texture, pourability and mouth-filling chocolates. And caramel topping leverages shear thinning or thickening effect for easier manufacturing, packaging and consumable. So, food items, blood and drug delivery, all these things are non-Newtonian fluids. So, here in the non-Newtonian shear thickening is this behavior. Shear thickening, you see here, the slope increases with respect to rate. So, all these things are non-Newtonian fluids. Asphalt, blood, glue, corn flour with water, sperm, then lava, molten metal, toothpaste, whipped cream, gypsum paste, paint and ketchup. All these things are non-Newtonian fluid. They can have a shear thinning or a shear thickening behavior. Compressible fluid. A fluid is considered compressible if its density changes significantly. This change in density are typically due to the variation in pressure or temperature. The gas are inherently compressible. Their density is highly variable and changes significantly with the modest change in the pressure and temperature for compressible fluids. The compressible flow is quite common for gases, especially at high speed. Compressible flow is quite common for gases, especially when the speeds are in Mach greater than 0.3. The analysis of compressible flow often focuses on gas dynamics. When liquid behaves as compressible fluid, under certain extreme conditions, the liquid can exhibit compressible behavior. So, this is for an incompressible fluid flow, this is for a compressible fluid flow. This is predominantly gas and this is predominantly water. This typically requires either high pressure on the order of 1000 atmospheres for water or achieve velocities comparable to the liquids which are speed of sound. So, then at a very high velocity or very high pressure, then it starts behaving like a compressible fluid. Another important consequences of compressibility of fluid is that the disturbance introduced at some point of the fluid propagates at a finite velocity. So, you drop a stone in water, the wrinkles form, right. For example, if a fluid is flowing in a pipe and a valve, which is their exit valve, is suddenly closed, the effect of valve closure is not felt instantaneously upstream. So, it takes a finite time for the increase in pressure created by the valve closure to propagate to the upstream location. So, for example, you have a pipe and then the water is flowing through a pipe, you are closing the pipe, and then what happens after a period of time, there is pressure increase and then you can see the fixture gives off between the pipe and the tube. So, if the fluid is flowing in a pipe and a valve at the outlet is suddenly closed, the effect of the valve closure is not felt instantaneously upstream at the pipe. It takes a finite time for the increased pressure created by the valve closure to propagate to an upstream location. That the speed of sound is related to change in pressure and the density of the fluid medium through this equation. Incompressible fluid. An incompressible fluid is an idealized fluid where the density rho is treated as a constant. This means that the density does not change or the change is very negligible with respect to pressure and time, which is quite common for fluids. All the liquids are treated as incompressible fluids because the density changes very little. The liquid have very high bulk moduli, which means that there are resistance to change in volume. For instance, the density of water increases by 1% when you increase the pressure by a factor of 220. For many practical engineering applications involving liquid, the variation of density is negligible. So, this is the liquid surface which is there, and these are the specific weight gamma. The pressure in a homogeneous incompressible fluid at rest depends only on the depth of the fluid related to some reference plane. It is not influenced by size or shape of the container in which the fluid is held. Thus, in image, the pressure is the same. The pressure is the same, you take it at the top or you take it at the line AB. Thus, in image, the pressure is the same at a point along a line AB, even though the container are irregular in shape. So, it is like this, a glass or something like this, or a scent. This is a scent bottle and this is a bottle filled with oil. The actual value of P along AB depends only on the depth h, the surface pressure P and the specific gamma of a liquid in the container. So, in this chapter, friends, we saw what is a fluid, what is the important property, what do you understand by Newtonian fluid and applications of Newtonian fluid, non-Newtonian fluid, types of non-Newtonian fluid, and finally, compressible and incompressible fluids. These are the references which we have used, and thank you very much.